When you're sitting in a calculus class, sometimes it's hard to see how all those symbols and ideas connect to the real world. Well, today we're going to change that. We're going to fire up a massive industrial furnace and see one of the biggest ideas in calculus, the rate of change, in action. We'll see how engineers use this exact concept to control incredibly powerful machines. Let's jump in.
Okay, so first, let's get a look at our furnace. It's a pretty simple setup based on a diagram from our source. You've got the burner, that's what's making all the heat, and then you have these refractory bricks lining the whole thing. They're designed to take some serious temperature. But the most important thing for us, we have some real data from this thing, telling us exactly how it heats up over time.
So this gets us to the big question. Yeah, we know the furnace is getting hotter. That's kind of obvious. But in the real world, just knowing that something is changing isn't enough. The question that really matters is, how fast is it changing? Understanding that speed, that rate, is what gives you real control. And that's exactly what we're going to figure out.
Now, before we start crunching numbers for this huge, hot furnace, let's dial it back. Let's think about something way simpler, something you've probably done a million times: filling a bathtub. It might sound totally unrelated, but trust me, it's the perfect way to build up our intuition for this.
Okay, let's put these two side by side. For the furnace, we're measuring temperature in degrees Fahrenheit, and we're watching it change over a certain number of minutes. For the bathtub, we're measuring the volume of water in gallons, also over a certain number of minutes. You see the pattern here? What we care about is degrees per minute for the furnace and gallons per minute for the tub. The stuff is different, but the idea, how much of something changes over time, is exactly the same.
All right, hopefully that bathtub analogy makes sense, so let's take that same logic now and apply it right back to our industrial furnace. We're just going to swap out gallons per minute and start thinking in degrees per minute. Same idea, just with heat instead of water. So let's take a look at the actual data we have.
Here it is. This is the real data from our source. So at 9:45 in the morning, an engineer checks the temperature and writes down 1255 degrees Fahrenheit. Then, a little bit later, at 10:32 a.m., the reading is up to 1276 degrees. And believe it or not, these two little measurements are everything we need.
And if you're a visual person like me, this bar chart makes it really obvious. You can clearly see the temperature at 9:45, and then you see it climb by 10:32. That difference, that gap between the two bars, that's the rise we're interested in. And figuring out exactly how big that rise is, well, that's our very first step.
So how do we take those two data points and turn them into one useful number, that rate of change? Well, the formula we're going to use is actually super straightforward. Let's just walk through the 3 simple steps to get our answer.
Here's the game plan. It's just a 3-step process. First, we're going to figure out the total change in temperature, which in math speak we call delta T. Second, we'll figure out how much time passed, which we call delta T. And finally, we just divide one by the other, the change in temperature divided by the change in time. That's it. That's the average rate of change.
Let's tackle step 1. Finding delta T. Now, that little triangle symbol, that's the Greek letter delta. Whenever you see it in science or math, it just means the change in something. So to find the change in temperature, the formula is simple. You take the final, hotter temperature and subtract the starting, colder temperature. Okay, time to plug in our numbers. We take that final temperature, 1,276 degrees, and we subtract the temperature we started with, 1,255 degrees. This one little calculation is going to give us the total temperature climb.
And there we have it. The answer is 21 degrees Fahrenheit. So, between those two measurements, the furnace got exactly 21 degrees hotter. That right there is our delta T. Step 1, done.
On to step 2, finding the change in time, our delta T. So, the first reading was at 9:45 a.m. and the second one was at 10:32 a.m. The question is pretty simple. How many minutes passed between those two times?
Turns out 47 minutes went by between 9:45 and 10:32, and that is our delta T. So now we have both pieces of our puzzle, right? We have a 21-degree temperature change, and we know it happened over a period of 47 minutes. We are ready for the final step.
But before we do that final division, let's just pause for a second on this idea. The number we're about to calculate isn't just some random piece of data. It tells a story. It's the story of how that furnace's temperature was behaving, on average, during that specific window of time.
And here we go, the grand finale. We take our total change in temperature, that delta T of 21 degrees, and we divide it by the total time that passed, our delta T of 47 minutes. You pop that into a calculator, and what do you get?
about 0.447 degrees Fahrenheit per minute. So what does that mean? It means on average that furnace was getting hotter by just under half a degree every single minute.
So we did all that work and we got a number, 0.447. But so what? Why does an engineer, or anybody really, care about that number? This is where this whole thing stops being just a problem in a textbook and becomes a genuinely powerful tool.
I mean, really think about it. If that furnace heats up way too fast, those expensive refractory bricks could crack. That's a huge safety problem, not to mention a disaster for the budget. That's material integrity. If it heats up too slowly, you're just burning fuel and wasting money. That's an efficiency problem. And if you're trying to treat a piece of metal in there, the rate of heating completely changes the quality of your final product. So this one little number, it actually affects everything.
Okay, you've seen how it's done. Now it's your turn. You know, the absolute best way to make a new concept really stick is to try it yourself. So let's work through a quick practice problem together.
Here's a new situation for you. This time, a furnace is actually cooling down. It starts at 1500 degrees, and 30 minutes later, it's at 1425 degrees. So what's its average rate of change? Now here's a little hint. Because the final temperature is lower than the starting temperature, your delta T is going to be a negative number. And that just means your final answer will be negative too, which makes perfect sense for something that's cooling.
And while you're thinking about that problem, chew on this idea for a second. If you know what the temperature is right now, and you know the rate at which it's changing, you can make a really good prediction about what the temperature will be in 10 minutes or in an hour. This isn't just about describing what happened in the past. It's about predicting and even controlling the future.
All right, let's finish up with one last challenge just to lock this skill in. A pizza oven goes from 100 degrees to 400 degrees in 20 minutes. What's its average heating rate? When you can answer that, you're not just solving a math problem. You're using the fundamental language that describes how literally everything in our world changes. Thanks for digging in with us today.